Welcome to Solution Equilibrium. This goes along with the SE8 assignment, Maximum Dissolvable Amount. If we have the KSP value and a list of known ions in water, we can determine how much of an individual ion can be added before a solid will begin to form. Remember that the KSP expression lets us know the maximum dissolvable amount of a solid. So here's our KSP expression, and let's say I've got a beaker that's sitting on an electric stir. All right, so I'm going to add some water to that beaker, and then I add in a magnetic stir rod and turn the electronic stir on and start stirring up this solution. Now I'm going to chuck a little bit of solid inside there, so there's some solid dissolving. Nice stuff. Now let's say I didn't put that much solid in. So if I substituted in the concentration of the cation and anion, it would be very low. And let's say that that concentration I added is less than what the KSP value is. So the number on the green sheet is larger than the product of the concentrations once subbed into the KSP expression. Well, that means that the solution is not saturated. More solid could still be dissolved in the water. But if I add more solid so that when those concentrations are subbed in, they equal the KSP value, well, then that means I am now at the maximum dissolvable amount. Then the solution is saturated. No more solid could be dissolved in the water. But if I add even more solid, well, that will take us beyond the maximum dissolvable amount. When substituted into the KSP expression, well, that product is going to be larger than the number found on the green sheet. So if even more solid is added so that the KSP value is smaller than the product of the concentrations that have been added, then more solid has been added than the water can hold. If given time to settle, there would be solid sitting on the bottom of the beaker. Example 1. Will a solid form if we add sodium fluoride until its concentration reaches 0.0500 molar in Regina tap water, which already contains 45 parts per million calcium ion? Now, I worked out the molarity for you. So if it's 45 parts per million, that means that the concentration of calcium ion in Regina tap water is 0.001128 molar. Well, we've got calcium, and who would that form a potential solid with? Well, it is a cation, so it would form a solid with an anion, which would have to be fluoride. So the potential solid would be calcium ion coming together with fluoride, which would make CaF2. And if we do our balanced decomp reaction, well, there's what it looks like. And after we've done our balanced decomp reaction of the potential solid that's going to form, we can make our KSP expression. Now, we know the calcium ion concentration because it was given to us in the question, but we don't know the fluoride ion concentration. But we were given the concentration of sodium fluoride. So we're going to do a balanced decomp reaction for sodium fluoride. And if the sodium fluoride concentration is 0.0500 molar, and one sodium fluoride makes one sodium ion, and one sodium fluoride makes one fluoride ion, then the concentration of Na plus and F minus will both be 0.0500 molar. So our KSP is going to be the calcium ion concentration, which was given to us as 0.001128. And our fluoride ion concentration we have determined to be 0.0500 molar. Punch that into our calculator, and that gives us a grand total of 2.82 times 10 to the negative 6. Now I'm going to take out my green sheet and look up calcium fluoride. And on the green sheet, it says that the KSP value, the maximum dissolvable amount for calcium fluoride, is 3.2 times 10 to the negative 11, which is much smaller than 2.82 times 10 to the negative 6. So we have, with these concentrations, exceeded the maximum dissolvable amount for calcium fluoride. And if we've exceeded that number on the green sheet, then that means a solid will form in this situation. Example 2. What is the maximum amount of lead-2 ion that can be added to Regina tap water, knowing that it already contains the following: sulfate, chloride, and fluoride ions? So we have three potential solids that could form with the lead. The first one is lead-2 sulfate. So I will do a balanced decomp equation for lead-2 sulfate, breaking up into lead-2 ion and sulfate ion. From this, we'll make our KSP expression. And since the question asks us what is the maximum amount of Pb2 plus that can be added, we're going to isolate Pb2 plus in the KSP expression. So I divide both sides by sulfate, and the lead-2 ion concentration is the KSP number off the green sheet divided by the sulfate concentration that we've been given. I run that through my calculator, and I could add lead-2 ion to a concentration of 9.0 times 10 to the negative 6 molar. Once I hit that concentration, a solid of lead-2 sulfate would start to form. Now we also have chloride, so that means lead-2 could form a solid with chloride. So I'm going to write the balanced decomp equation for lead-2 chloride, breaking up into lead-2 ion and chloride ions. I make my KSP expression from that balanced decomp. I want to get Pb2 plus by itself, so I will divide both sides by the Cl minus concentration squared. And again, I will get the KSP number for lead-2 chloride off the green sheet, and I will divide that by the chloride concentration squared. Punch it into my calculator, I wind up with 2.3 times 10 to the negative 3 molar. The other possible solid is lead-2 fluoride. So I write the balanced decomp for lead-2 fluoride that breaks up into lead-2 ion and fluoride ions. I'm going to write the KSP expression from the balanced decomp equation, and then I will isolate Pb2 plus by dividing both sides by the F minus concentration squared. And for the last time, I'm going to get the KSP number off the green sheet for potassium fluoride and substitute that into my equation and divide by the fluoride concentration squared. And that gives me 1.3 times 10 to the negative 3 molar. Now it asked us again in the question, what is the maximum amount of Pb2 plus that can be added to the tap water? So we're going to start at 0 and work our way up. Now, right away, someone might say 1.3 times 10 to the negative 3, but that number is actually one of the larger numbers we have here because, well, let's take this out of scientific notation. Clearly, the very first number, 9.0 times 10 to the negative 6, is much smaller than 0.0023 or 0.0013. So that means if we're starting at 0 and slowly working our way up, the concentration we would hit first is 9.0 times 10 to the negative 6 molar. Once we hit that concentration of lead-2 ions, it would start to form a solid in our pipes of lead-2 sulfate. And that's it. You're good to work on the SE8 assignment, maximum dissolvable amount. I expect you to put in the maximum amount of effort so that you guys have the maximum amount of success when it comes to writing this assessment.